So, Dr. DS, Dr. Hello.
Audible.
Dr. D. Sreenivasarao. Hello. Hello. Dr. DS, sir. Can unmute yourself.
Oh, hello, sir.
Yeah, yeah. Are you ready, right, sir?
Yeah, you are audible, right?
Yeah, we're all. Yeah, good afternoon, everyone. Yeah, I welcome you back to the lecture 2 of the GIAN course on hybrid renewable energy system and microgrids. Yeah, now Dr. D. Sreenivasarao is a faculty from Department of Electrical Engineering, NIT Warangal. He is associate professor uh, and he works in the area of uh, high power converters. And now today he is going to deliver on power converter in microgrid application. I'm handing over to Dr. D. Sreenivasarao. You can go ahead.
So, good morning. Good afternoon, everyone. Let me share my screen. I hope my screen is visible.
It is.
Uh, okay. So, one of the main important point, especially for the renewable energy sources generation and integrating to the grid or operating as a microgrid, so is the power converters. Right. So this is essential for any renewable energy generation, integration, and connecting or operating in the grid connected mode or in island mode, anything, right? So normally, in many we have many power converters are there. So in case of renewable energy sources, so as we discussed in the morning, so they are normally classified into unidirectional converters and another one is the bidirectional converters. So depending on your application and exactly what you are integrating to the grid, right? So based on that, you will select the power converters. So basically, you are supposed to use DC-DC converters, right? Or else you need to use some inverters. So the same inverters will do the job of AC to or DC conversion and as well as DC to AC conversion. If it is a DC to AC conversion, so this is normally a conventional inverter. If it is doing the job of AC to DC conversion as well, so we normally call as active rectification or the front end converters. Okay. So this DC-DC converters again unidirectional or the bidirectional converters, right? And isolated DC-DC converter and non-isolated DC-DC converters are there. Right. So first we'll focus on the power converters, especially the inverter portion. So later on we will move to the DC-DC converters. Okay. So depending on the power available, what means how much power you required or how much power you're generating and the voltage levels. So we have several options for the inverters. So conventionally, if it's a single phase, we normally use the or we prefer the H bridge, single phase H bridge inverter or the off bridge inverter that is sufficient. If it is small rating PV or something, or maybe some 230 volts if you want to integrate to the single phase grid. So in that case, that is sufficient. So when it is a higher, slightly higher, in that case, we may go for the three-phase inverter, so which may be used up to a voltage of 400 or 415 volts, or even slightly higher than that. Maybe you can integrate to a 2.3 kV grid. But your requirement is you are integrating a bigger renewable energy source. Also, we have a bigger energy storage system, and you are handling with high voltages, relatively high voltage in the distribution line. Maybe you can use the voltages of 11 kV or so. In that case, we need to go for the other options. So basically, those are normally we can go for other options like multi-load inverters and so on. Right. So first we'll start with the basics of power converters, and next we move to the high power inverters, and we will discuss some of the conventional topologies of multi-level inverters, and later on we move to the reduced switch count multi-level inverters and time pyramids, maybe in the upcoming sessions. So we'll discuss about their PWM schemes and the what are the challenges so we have, so especially when you are integrating to the grid. So those things are also discussed maybe in the next section. Right. So first thing is that, so as we know that, right, for any application, any power converters, you require some cost-effective converter. So that is a prerequisite. The application may be of anything. It may be a motor drive, or it may be a renewable energy source integration, HVDC effects, anything, right? We normally require one power converters. So one is the cope with the variations of the input DC voltage, and another one is the regulating the output of the converters, and another one, in case of motor drive applications, we need to maintain the VBF ratio constant. And in case of applications like the renewable energy sources or the FACTS applications, in that case, we need to operate the converter in the controllable current source or the controllable voltage source, depending on the your requirement. Right. So this point, most of the times we need to use. That means you are operating the converter as a controlled current source or controlled voltage source for the grid integration, or operating the converter as a grid forming inverter. So there are many applications are there. So one is adjustable speed drives, electric vehicles, facts, DSTAT, the custom power devices, active power filters. And this is the point where we are focusing right now. One is the renewable energy generation. So this, for renewable energy generation you require, for integration you require, and for control of that one, so that also require the power electronic circuits. So we have HVDC and HVDC light or HVDC plus, and the grid connected transformer less application. So normally if you are integrating to 11 kV distribution grid, in that case you typically require a convert or transformer. So by using these multi-level inverters, somehow we need to eliminate this transformer completely, so that so we can design the converter to a full voltage level. Right. So battery charges for the electric vehicle or for the battery energy storage systems, and home appliances like the refrigerators, air conditioners, and handheld tools likewise. Right. So we have several converters are there. So like power converters, one is the AC to AC converter, direct converter. It will be indirect conversion. So AC is converted to DC first, and DC is converted back to AC. So applications like the motor drives, so we normally require AC to DC, and again DC to AC. Similarly for wind turbine, we also require this AC to DC, and again DC to AC, so which can ultimately integrate to the grid. Right. So we have two options are there basically. One is the voltage source and the current source. So current source, early days we especially useful for the motor drives and HVDC applications. So one is the line commutated inverters and the PW current source inverters. These are popular. So most of the, and another, nowadays we are not no longer using these kind of converters. So now we move to the voltage source inverters. So depending on the power levels we are using, so we have two-level inverters are there, and multi-pulse inverters, and multi-level inverters are there. So these multi-pulse inverters are used for the high voltage applications like FACTS and HVDC. So we have 48 pulse converters and 24 pulse converters. Likewise, we have. And come to this multi-level inverters. So these three are the conventional multi-level inverter topologies. And later on, from the past 5-10 years, a lot of research is happening here. So we have so many inverter topologies are there. So more than 1,000 inverter topologies right now. They are we can see we can means those are available in the literature. So everything some small changes in the switching arrangements, or the reducing the blocking voltage, or reducing the switch count, or in that case increasing the modularity of the inverter. Right. So whatever the challenges that are present in uh, these conventional multi-level inverter topologies, those things are addressed in those topologies. Anyway, we'll discuss those things in the later point of the in the session. Right? So basic thing is that so voltage source and the current source inverters. So compared to the current source inverter, so voltage source inverter is popular. So one reason is that so we normally require a large inductor here, so that is bulky and also associated with the losses. Whereas here normally you require a DC source. The DC source can be obtained from a AC to DC rectifier circuit, or it may be some front-end converter or active rectifier circuit, like with power factor correction. And also it may be a battery, or it may be a PV, or it may be the output that is generated after converting into DC from a wind turbine, likewise. Right. So whereas here, in case of current source inverter, usually the losses, switching losses are more. So why? Because here both switch and the diode will conduct same time. So both will carry the load current. So whereas here, so depending on the mode of operation, so either the switch will conduct, or the this diode will conduct. So that means the losses will be less when compared to the uh, uh, current source inverter. So the only advantage with current source inverter is its short circuit protection. So when some dead short circuit across one phase lag, in that case the current will be equal to the source current. So whereas if short circuit occurs here, the impedance, that means we have voltage source, so we are short circuit there. So we have so means theoretically, you will get infinite current, and it will damage the switching devices. Obviously, this can be prevented so by adjusting the firing pulses between these two, or by maintaining some delay between the upper and the lower devices. So this can be overcome. Right. We normally keep 1 or 2 microseconds time delay depending on how much frequency your operation. Typically, if it is a 1 kHz frequency, so we normally use 1 microsecond. Your frequency is too high, in that case, it is in the order of a few nanoseconds. So what we concluded is that so here so voltage source inverter is well matured, and compared to CSA the losses are less. So therefore, so most of the applications nowadays we are using only the voltage source inverters. Right. So conventional voltage source inverter, or this voltage source inverter three phase, it is also known as the two-level inverter. So by exactly it is known as two-level inverter means so if you measure, let's say if you consider some fictitious thing, like something like this, right? This one will be assumed this is VDC, and this is VDC by 2, and this is VDC by 2. And if you measure the voltage between these 2 points, so if this top switch is on, you will get the VDC voltage, and if this bottom switch is on, so we'll get the minus VDC by 2 voltage. Or else that means you will get two voltage levels here, or else we can analyze in a different manner. Let us assume this one is the VDC. Right. So this one is A phase, and this is the DC link or negative bus. And if you measure the voltage between VAN, or if it is VAN, so if the top switch is on, you will get VDC voltage, and if the bottom switch is on, you will get the zero voltage. So that means you are getting the two levels. So that's why it is known as a two-level inverter. Right. So you are aware that, right? In this two-level inverters, so we don't have the phase voltage here, or there is no phase voltage of the inverter. So only we have the line voltage. If at all you require a phase voltage, so you need to connect some load here. So that load, the neutral, if it is a load is a star connected, the load side neutral star connection. so will act, or from that you can access the load phase voltages, but not the inverter phase voltages. So most of the times we use the to control these inverters, we normally prefer the methods, like there are two control methods, PW methods are there. One is the current control method and the voltage control method. So in case of voltage control method, you require a modulating signal, right, and some carriers. So by comparing the carrier and the modulating signals, the switching or the firing signals is generated for the each phase, right? And that is thing, and the inverter will operate as a controlled voltage source, right? So whereas if you want to use a current control for the inverter, right, in that case we have some methods are there. One is the hysteresis current control and the triangle carrier current control. In that case the inverter acts like a current source, right, and the in other words, in inverter acts like controlled current source, so we can control the current flow inside the inverter, right? So depending on applications, sometimes we use the voltage control methods, or sometimes we use the current control methods. And if you are for most of the times for voltage source inverter, if you're using a current control voltage control methods, we normally prefer the sine PWM technique, or else we need to use space vector modulation techniques. These two are popular methods. There are other methods as well, like the selective harmonic elimination and all. So those are not very much familiar, especially from the renewable energy point of view. They may be used for the application like motor drives. Like, so if you are using a conventional, in other words, sinusoidal PWM technique, so this is the method, and you can see that the huge value of THD here, and also we have some sideband harmonics, which are centered around the frequency modulation index MF. Right, we have 20. If it is MF is selected as 20, we have 20th order harmonics. So this will be around 18th harmonic, and this may be 22 second order harmonics. So that means you have even order harmonics are there. If you make MF as 21, in that case, we can eliminate the even order harmonics as well. Right. And another thing is that uh, so we have high value of THD. So to make this one, so normally if you directly fed this one, right, so that the grid may not accept this voltage, so therefore somehow we need to filter this one. So normally we prefer LC filters or LCL filters or LCLC filters are normally preferred. So depending on what things are there, most of the times we prefer the LCL filter. The design is slightly simple. So by connecting these filters, the waveform will be more or less sinusoidal, and we can also reduce its THD value so that we can easily integrate to the grid. So now the point is that if you are using it for high voltage applications, like high voltage applications, what are the things we need to care is that, so one is the high power two level inverters. So if you go for high power two level inverters, so let us assume that I am for the same inverter I consider, right? So let us assume I want to integrate to a 11 kV grid, right? So in that case, if it is 11 kV, so that means accordingly, so this this capacitor or this voltage source we need to select. You know the basic things, right? If you are using a sine PWM technique, right? If your voltage, if you want line voltage here, this is the V line voltage. So accordingly, so we need to select the DC link voltage. So that means this DC link voltage will be V line. So your line voltage RMS value divided by 0.612. So that is the DC link voltage that you require. If you are using a sine PWM technique, if you are using a space vector modulation technique, in that case we normally use 0. V line by 0.707. Right. So that means if it is 11 kV, so roughly you require to use at least 18 kV on the DC side. Right. So that means each switch is supposed to block this much voltage, that 11 kV or 18 kV, 11 kV divided by this much voltage is supposed to block. All right. So that means these kind of devices are not available, as you know that, right? So far we have the devices, especially in IGBTs. Yes, 6.5 kV devices are available, and that can handle a 750 amperes of current. Whereas if you are focused on the current In that case, we have devices available for 2400 amperes and 1700 volts devices are available, right? This is based on the silicon based devices. If you go for the like silicon carbide devices, so those are the wide band gap devices. So in that case, the devices or means MOSFETs are available for 15 kV MOSFETs are available, silicon carbide based MOSFETs. Right, if we are using some silicon carbide based IGBTs, still it is in the research. So we have 25 kV devices are available for an N channel, and for a P channel, it may be 15 kV devices are available. Right. So now the point is that, so when you're using a wide band gap switching devices like the silicon carbide, so we can get the high voltage levels, means high voltage levels in the switches, right? But the thing is that, so these things are in the production, or the cost of this one is relatively much higher when compared to the IGBTs, silicon based devices. So therefore, for your requirement, so what you are supposed to do is that you need to connect several switching devices in series, so that you will cater the required voltage. Similarly, if you want to increase the current rating, so we need to connect several switching devices in parallel, right? So like this. So that means we have series connection of several switching devices. We need to connect in series, and another switching string of series connected devices. So that we need to connect here to increase its current rating. Right. But even though doing all these things, still it's look like a two-level inverter. So there is no change in the THD point of view. Right. And we need to give a common gate pulse for all the switching devices, right? So that means, for example, if some fault is occurred or some if device is failed, in that case there are two options. Normally when the device is failed, it will be either short circuited or it is open circuited, like what is the construction of the device. If it is a bond wire based switching devices, in that case the device will be open circuited. If you are using some springs, or right, in that case inside that, so in that case the device will be short circuited. So most of the times we prefer the short circuit, so whenever the device is faulty, right? So that means if the device is faulty, this is short circuited, so now these two are supposed to withstand the full voltage. So that means the burden across the switching devices will be high. So therefore, we normally keep some redundant switches, like 10% of the redundant switches we normally keep in a string. So for example, if three switches are there, instead of three, we normally use one more switch here. So one device is faulty, so that the burden will be shared among the other healthy devices. Right. Same thing for the current as well. The drawback with this one is the number of switching devices are more, but the performance point of view, still it's like a two-level inverter. Obviously, if you're designing a filter like LC filter for a huge voltage like 11 kV, the size of the inductor, capacitors, and their isolation and all those things will be much bigger, right? And it also cost size and as well as the weight. Right. So these are the drawbacks. So when you're using a two-level inverter for these applications, sometimes what we normally do is that, so when you're integrating to the 11 kV grid, we normally use connect some transformer in between. The converter is of some low voltage rating, and the transformer will be of means the grid will be of 11 kV or something. The means actual converter is low voltage, and here if you're connecting like that, so we no need to worry about the voltage, but we need to worry about the current. So the same, for example, we are increasing the current, so therefore we need to connect several switching devices in parallel. Right? So therefore another option, so which one is the multipulse converters? So where in case of multipulse converter, several 6 pulse converters, like 6 pulse inverters are connected in series parallel, right? Let us assume this is 12 pulse converter here. So we have the phase shift between these two converters of 30 degrees here. So that phase shift is produced by the 12 pulse converters. You might have familiar with this one when you are studying the HVDC. Right, this one is 18 pulse converter and this is 24 pulse converter. So depending on your requirement, so this outputs of this one will be connected in series and outputs will be connected in parallel. Right. So if it is a series connection, we will it will reduce the ripples in the output voltage. If it's a parallel connection, it will reduce the ripples in the input current waveform. So here the main drawback of this multipulse converter is that it requires complex phase shifting transformers like zigzag and polygon transformers are required. And another thing is that so whenever you have transformer, so obviously you and the other side you have the uh, power electronic circuits. So obviously the thing is that the currents it will handle is non-sinusoidal. So when it is non-sinusoidal, so first thing is that so we need to derate these transformers. You remember some K factor, right? So we need to derate the transformers. In other words, you might have studied the transformer utilization factor TU here. So accordingly, you need to derate the transformers because they are handling the non-sinusoidal currents. Right. And another thing is that if some small portion of DC offset is there, some DC quantities are there, this transformer leads to the saturation and it draw more current in the for producing the magnetizing circuit, and that leads to the lower efficiency. Right. And another thing is that this transformers will always means it will be up to 50% of the space or more than 50% of the space, weight, and their cost as well. Right. So that's why this is normally used in HVDC and the FATS applications. By using this, we can directly, maybe you can go up to 220 kV or even higher than that. You can integrate to it. So nowadays, this HVDC also no longer using. So by using some modular multi-level converters, so this problem of using transformer is we can overcome. So next we have the multi-level inverters. This is how multi-level inverter is generated. Right, we'll quickly complete this. So let us assume that we have one DC source and one switch is connected and that switch is toggling between this A and 0. Right, and you are measuring the voltage across VA0. Right, we are measuring the voltage across VA0. So let us assume the switch is connected here. In that case, if you measure the voltage across VA0, you will get this VDC voltage. And the same switch, if it is connected here, you will get the 0 voltage. So that means we will get VDC voltage here and this 0 voltage here. So this is how you produce the two-level waveform. This is same thing what we seen in a two-level voltage source inverter. All right. So now I took two DC sources and there is a split between these two DC sources and I have access for the midpoint of this one. All right. So now I have three things are there, three positions. When the switch is A, this position is the switch is at position 1. In that case, so if you measure the voltage between VS0, so you will get this 2 VDC voltage. If it is at position 2, you will get VDC voltage and you will get 0 voltage. That means by splitting this one, you are getting the 3 voltage levels. And if you keep on extending this one, like this is 1, 2, 3, 4, if it is connected to the 1, so all these things will come into series. So whereas if it is at position 2, so this one is bypassed. It is at position 3, this is bypassed. And this position is only we have this VDC voltage here. And if it is connected here and at this point, then you will get the 0 voltage. Right. So what we observed that, so when you have a multiple switches are there, when you have multiple DC sources are there, so by properly turning on and turning off them, so we can obtain a multi-level waveform. Right. If you observe when you compare these two waveforms or this waveform, so this is more close to a sinusoidal waveform. Right. Whereas if you compare these two, so this is much more a better approximation of a sinusoidal waveform. Correct. So when you are producing a sinusoidal waveform, means the THD of that waveform will be very much low. And another thing is that we can easily integrate to the grid, and also it reduces the filter requirement. Right. So here this is the good thing is that so we are using a small voltage steps here. So for example, this converter is of 2 VDC rating, but we are using only small DC sources. Right. So that is small steps of DC voltage sources. And another thing is that so if you are connecting a switch between these two, the blocking voltage of that switch is they no need to withstand the full voltage. All right. The switch may not no need to withstand the full voltage. So only a portion of the voltage or this voltage is supposed to, the switch is supposed to block. But even though the converter is of let us assume this is of this much high, like if you have one more source is there 4 VDC, in that case each switch is supposed to block only VDC voltage, not the entire DC link voltage. Right. So this is some advantage here. So we can get the high output voltage with matured medium semiconductor devices. The point is that no need to go for the high power semiconductor devices. Whatever the adjusting thing is there, so those are sufficient. So we have reduced the CMI effect and the filtering requirement. The waveform is more close to a sinusoidal, so no filtering is required. And they draw the input current with lower distortion. If the application like AC to DC conversion, in that case they will draw low input current and reduces the common mode voltage. So this is the voltage which is common across all the switching devices. So if the waveform is this phase voltage is all equal to a sinusoidal or close to a sinusoidal, in that case if you add all the phase voltages, you normally get less value when compared to a two-level inverter, and they can operate at lower switching frequency. And another thing is that they're fault tolerant if some fault is occurred, so we can reconfigure the inverter to operate at same power level and voltage level, or else some reduced power and voltage levels, and they're less prone to failure and their cost is relatively low when compared to the multipulse and high power two level inverter case. Right. So these are the advantages here. And as we discussed, there are three benchmark topologies are there. One is the neutral point clamp, also known as the diode clamp. Another one is the flying capacitor and cascade edge bridge inverter. So out of these three, so these two are very much popular. And whereas this flying capacitor is not relatively less applications here. So this is especially used in the traction drives, right? All these traction motor drives, they normally use this flying capacitor or multi-level inverters. Right? So come to this three-level neutral point clamp, also known as the diode clamped multi-level inverter. This is the structure. So we have two DC sources are there, and we have a midpoint access to the midpoint, right? And this is A phase, B phase, and C phase, right? So these are A phase, B phase, and C phase. And here the operation is slightly simple. This S1 and S3 are complementary here, and whereas S2 and S4 are complementary here. Right. So this switch and this switch is complementary. This switch and this switch is complementary. Right. So 1 and 3 are complementary and 2 and 4 are complementary. The operation is very simple. So you can access this VAZ. Right, that is one way to analyze the circuit. So if VAZ, right, if this is turned on and this is turned on, right, so this is now A, so these two are on, right, so that means A is so this A point is connected here, right, this A point is connected here, so therefore, so we will get so E voltage here, right. Similarly, if this is off, right, this switch is off, this both are off, mean off, on means these two are off, right. Similarly, this switch is off, right, this switch is off, that means this switch is on and this switch is off. So as we discussed, S1 and S3 are complementary and S2 and S4 are complementary, right. So now if you observe that, so depend if this one, so this D2 is this S2 is conducting and S3 is conducting, but if you see that these two are the diodes which are known as the clamping diodes, all right, so these are clamped to the this neutral point generate, that's why it is known as the clamping diodes. So here, so we have only one path depending on the current direction. Let us assume that the current is flowing in this direction, all right, so in this direction the current will leave like this from this neutral point to like this, right. So that means between A and Z, so you are getting a zero voltage, but the thing is that so dZ1 is conducting, dZ1 and S2 are conducting here, right. So whereas if the current is in the other way like this, if the current is flowing like this, see it is the current is flowing through this switch S3 and the diode this one. So now you are getting the 0 voltage, but now it is DZ2 and S3 are turned on. So depending on the current direction, like it is from the source to load or from the load to source or the during freewheeling time, so we have 0 voltage, and at a time a one diode will be forward biased and it will carry the current. Right. So now if both switches are turned off, so this is off and this is off, this is on and this is off. So now if this voltage is connected here, so that means between A and Z, so between A and Z, you will get the minus E voltage. So that means you are getting E voltage, 0 and minus E. So that's why it is known as a three-level inverter. Right. So depending on the number of levels in the phase voltage, so we normally say it's a three-level inverter. So typically if it is an M-level inverter, that means M levels in the phase voltage, right? So that produces a 2M minus 1 level in the line voltage. It is a maximum value. So why it is maximum value? You know that the difference of two phase voltages, right? So that gives you the line voltage. Sometimes this is only happen so when maximum, let us assume this is varying from E and 0, right? So these are the phase voltages. So whereas line voltages will vary from 2E 0, so 2E E 0 minus E and minus 2E, right? So why? Because so this is producing E0 minus E. So this is also producing E0 minus E. This is also producing E0 minus E. So if you are differentiating the, you are subtracting these two, right? At that time, let us assume this voltage is E. At the same time, this voltage is minus E. These two, if you subtract, you will get the 2E voltage, right? So that means this is operating at the highest value. If it is operating at the lowest value at the same time, you will get the 2E value. But if you are increasing the number of levels, so both will not be simultaneously happen. So therefore, you can reduce the number of levels. So meaning is that let us say if you consider level inverter, so there is the level levels in the phase voltage. So from this formula, you are supposed to produce 21 levels in the line voltage, but you may not get 21 levels. So roughly you will get 11, 19 levels, or likewise, or 17 levels you will get, right? So the point is that so the number of levels means the phase voltage number of levels, and you have a maximum of 2m minus 1 levels in the line voltage. So if you want to extend this to high number of levels, so if you want to extend this to more number of levels, so that is relatively simple. So just increase one more DC source, right? Increase one more DC source. So now you have three switches here, three switches here. This is for 4 level, and this is 4 DC sources here. And so we have 4 switches on top and 4 switches on the bottom. So that will generate the 5 levels. Right. So you have access to this midpoint here between 1 and 2 DC sources. Between 2 and 3 DC sources, we have like this X here, Y here, and Z here, and these are accessed through the clamping diodes. So these are known as the clamping diodes. Right. And these clamping diodes usually have some different rating. For example, this point X it is connected, right? If you see this one, this is connected between this point, right? If you observe, this one is connected between these two. So this DZ1, which is connected between these 2 points. So if you see here, this D1 is written, right? So that means if you see this one, so which is between here and here, right? So this is D1 dash into 2. So meaning is that, so this diode, whereas this diode, this high rated diode, is supposed to withstand, so this voltage only, right? So whereas this diode, so whereas this one, so this diode is supposed to withstand, this is connected between this point and this point, right? So that means this is if this is on and this is on, right? In that case, what happens is that this is supposed to withstand this 2E voltage. So that's why it is written as D1 into 2E. So meaning is that we have one more diode of same rating, so which is connected in series. Same thing here also, it's D1 into 3 means there are 3 diodes here because they are supposed to be stand at a different voltage level. Right? So here if you add or if you see that, right, the actual thing is that we have 3 diodes here and we have 3 diodes here. So that we have 6 diodes is required per phase, and here you have 4 diodes. So this is 4 diodes, and this is another 4 diodes. So 4 into 3 you require 12. So typically you require m minus 1 into m minus 2 diodes, right? So m minus 1 into m minus 2 diodes per phase you require. Alright. So this is one of the drawback of the diode clamped inverter. As you are increasing the number of levels, so the voltage across the or the number of diodes increases. And another thing is that in some applications, like for example, you are considering a PV here. So here we normally connect one PV here and another PV we normally connect between these two, like PV along with the MPPT. Or else some applications like if you consider some wind turbine application, like wind turbine application, somewhere this is the DC link that is you are producing here. So this DC link is come from, this is the wind turbine generator. So this is the thing, right? So it's producing like this. You have the rectifier circuit here. So this rectifier circuit is doing the job of AC to DC conversion, and this is the DC link. So we obtained, right? So this is the DC link you are obtained. So from this you are generating the 3 phases. So the 3 phases is integrated to the grid. So now the thing is that, so we need to balance these two capacitors, right? So let us assume this voltage is 2000 volts, right? So these two DC links are supposed to be, this is supposed to be 1000 and this is supposed to be 1000. If it is not 1000, right? So let us assume some deviation is there. Let us assume this is 950 volts and this will be 1050 volts. If this deviation is there, the waveform has some DC offset, right? And sometimes what happens is that this capacitor will be fully charged and this capacitor will be undercharged. So why all these things happen is that we don't have a control over it, right? Because depending on the current direction, so this capacitor will be charged or discharged. So this problem is known as capacitor unbalance or the neutral point voltage balance. Right. So there will be some deviation in the capacitor voltages because the charging and discharging times are not uniform. That leads to the deviation here. So that deviation, what happens is that sometimes if it is not properly addressed, so one capacitor voltage will be increasing like this and another capacitor voltage will be decreasing like this. Right. So therefore, we have some other alternative methods or other alternative circuits are there. So one alternative circuit is like this. This is how what we are discussing about. So let us assume this is a wind turbine here, and this is the grid here. Wind turbine, not exact wind turbine or generator, right? With wind turbine generator side, right? Or induction generator here, right? So we have, let us assume this is a six level inverter. So this is known as the AC to DC conversion. So this is the DC link here, right? So from this DC link, so it is connected to the motor or it is connected to the grid, right? So now the thing is that, so we need to properly balance these capacitor voltages. If at all not balanced, that balance is reflected on the output voltages. Okay. So therefore, we normally having some other alternative circuits. So this one is AMPC, so which is known as active neutral point clamped capacitor. So instead of capacitors, so we now replaced instead of diodes, now we replaced with the active switches. Okay. So all these things are replaced with active switches along with the anti-parallel diodes. Right. So now we can actually control the current flow. So depending on your requirement, so we can turn on this switch or this switch, right? So we can balance the capacitor voltages. So this is how we can improve the performance, or we can balance the capacitor voltages or the DC sources. Right? So this is one way. So another alternative, this is commonly used nowadays. So this one is known as the T-type topology or the T-type inverter. So this is especially used nowadays. Lots of applications are there. This is normally found in any application like the energy storage systems, especially battery energy storage systems, and the, sorry, electric vehicles. Electric vehicles in case of Yes, level 3 charges up to 350 kilowatt or even higher than that. So we normally found this kind of converter circuits, right? So which is known as the T-type inverter. So this is an alternative for the diode clamp multi-level inverter, and also alternative for the active neutral point clamped inverter. So this one, what we discussed, is known as the active neutral point. This neutral point is active. Earlier you have diodes are there, so now you replace with active switches. So that's why it is known as active neutral point clamp. So the drawback here is that, so these are the additional switches, right? So if it is an additional switches, again you need to control these switches, right? We need to write some uh, control method so that, so we need to recover the capacitor voltages. Alright. So another, as we discussed, so this one is known as T-type or a half-leg T-type topology. So nowadays mostly we call this as a T-type topologies in general. The circuit is like this. So again, we have two DC sources are there, right? And between these two things, right? So we have a this one, so which is known as the bidirectional switch. In other words, it's a four-quadrant switch. So this is known as the four-quadrant switch. So if you observe that this is four-quadrant switch. So that means it can block the voltage in both directions and allow the current in both directions. So this one is a two-quadrant switch. So whereas here it will block the voltage in one direction but allow the current in both directions. This way you can allow and this way you can allow through the IGBT and through the diode. But in block only voltage in one direction. But whereas this combination can block current in both direction, can block voltage in both direction. Right. So that means depending on this one, either these two will conduct or these two will conduct. Okay. So these are known as the bidirectional switches. Sometimes we in nowadays market, so this entire thing is fabricated in a one single device. Normally the symbol for this bidirectional switches are like this. So there is some extra line here for the IGBT, same IGBT symbol, but we have some extra line like this, like some extra line here, like this. So this is the IGBT symbol, right? We have some extra line here. That extra line represents it's a bidirectional property, bidirectional voltage blocking property. So normally if you see this one, so this one is the common emitter configuration. This is emitter, right? Common emitter configuration. So this one is the collector, emitter and the gate, right? So this is the common emitter configurations. In case of MOSFETs, we normally prefer a common source configuration. So this, if it is a MOSFET, this is source, and this is drain, and this is drain, and this is the gate, and this is the gate of the MOSFET, if it is a MOSFET. Okay. So why we prefer this common emitter? So because if it is a common emitter, so we normally have one gate driver circuit is sufficient. If it is why? Because the gate driver or the gate pulse is given between the gate and the emitters, right? If you are combining these two emitters, so that means we can give a common pulse with a common gate driver circuits. If it is like if you are connecting a common collector configuration, right, in that case you need to give isolated gate drivers for each device in this group. Right. So now the point is that uh, here this switch and this switch as a complementary. Right now the operation is pretty simple. When this switch is on, between here measuring voltage between this A and 0, you will get this VDC2 voltage. Let us assume this is also VDC. This is VDC voltage, right? VDC voltage. And if you turn on this switch, you will get the VDC voltage. Right. So if you turn on this switch, so depending on the current direction, we can control over it. So you will get the 0 voltage and you will get the VDC 0 and minus VDC voltages. Right. So when if you compare to the diode clamp, you can see that this circuit is like using lesser switching devices, right? Lesser switching devices, that is a good thing. And also we can balance the capacitor voltages. But some drawback is there, right? This switch is there, right? This switch, in case of diode clamp, two switches are there. Now we replace with only one switch. But the thing is that this switch, let us assume this switch is off here and this switch is on. So in that case, this switch is supposed to block these two DC sources. So that means this is supposed to block VDC voltage. So this switch is also supposed to block 2 VDC voltage. This is 2 VDC voltage. But whereas this switch is supposed to block only, this entire thing is supposed to block VDC voltage. So that means it will share, right? It half of the voltage will be shared by one this page, this one half of the voltage, this half of the voltage. Right? Right. So compared to the diode clamp, maybe the switches are rated higher, but the point is that you will get the more benefits, or you can reduce the conduction losses when compared to the diode clamp. So that's why the circuit topology is extremely popular in application like the energy storage system, PV, and the electric vehicle drivetrain, and also electric vehicle chargers, fast chargers. Also, we'll discuss also, if time permits, we'll also discuss the dual active bridge converter, DC-DC converter. So nowadays, the dual active bridge converter is also replacing with this three-level, this T-type topologies. Right? Yeah. So next, we quickly move to the cascade H-bridge inverter. Right. So this one is another multi-layer inverter, so which is very popular. Right. So here multiple H bridges are connected in cascade. So this is one H bridge, this is another H bridge, likewise it is connected. So each one, this one is producing some VH1 output, this is producing VH2 output. So these two outputs are connected in cascade, and this forms this A phase, this is VAN. So this forms the A phase, alright, VAN. You know that, right? Each H bridge will produce voltage levels. So each one will produce three different voltage levels, like this E voltage, 0 and minus E. So this is producing E, 0, minus E. So if it is producing E voltage, and at the same time this is also producing E voltage, like this is VH1 is E and this VH2 is E. So that means if you're combining these two, or if you're measuring the VAN, so which is equal to VH1 plus VH2. So now you will get the 2E voltage, right? So one bridge, if you're operating at 0 and another one is at E, you will get E voltage, and this is at maybe you have different options are there if you want 0 voltage, right? So this bridge may be operated E, so this is minus E, or this is minus E, and this is E, and this is 0, or this is 0. You will get the 0 voltage. Again, lot of redundancy is there. For example, if you require 0 voltage, right? Either you need to turn on these upper devices, or you need to turn on the bottom devices, so that you will get the 0 voltage. So a lot of redundancy is there. So meaning of redundancy is for same voltage levels, if multiple paths are there, so that leads to the redundancy. So when you have a redundancy, the good thing is that so we can reduce the switching losses. We can optimize the PWM algorithm so that we can reduce the switching losses. Like, and also some other advantage there we'll discuss shortly. Right? We can also get the minus E voltage and minus 2E voltage, so that you will get the 5 levels in the output voltage. Right. So this entire thing produces 5 levels. In the line of phase voltage, the line voltage it is producing 9 levels. The line it will produce 9 levels. Understood? So here the good thing is that so each one, so these switches are rated only for E voltage, right? So whereas these switches are rated only for 2E voltage, even though the inverter is rated for the 2E. So between these two, you have 2E voltage is the maximum, but each HP is supposed to withstand only E voltage. Right. So we have two options are there. One is the symmetrical and the asymmetrical. We have different voltage ratings as well. If it is 2E, right. So this is producing 2E, 0 and minus 2E. So this is E, 0 and minus E. So this is known as the asymmetrical cascade H bridge. That all are 2E. Right. All are 2E. Right. So now we can, if you observe, this is E and this is 2E, right? So they can produce 3E or 2E voltage, likewise you can produce the 3E. So with the same thing, you can go the 7 levels, right? So maybe you can try for another ratio, like minus 3E, you can also try. So this is minus 3E, so this is 0 and minus 3E. So with this, you can produce one more voltage like 4E and minus 4E. So that means you can get the 9 levels. Right. You cannot extend this one. Like for example, you try minus 4e. Right. If you're trying minus 4e plus 4e, this is 4e and 0 and this is minus 4e, right? So with these six things, right? So 5e you can get if you combine add plus 4e, e gives you 5e, and 4e minus 4e you can get. So 3E you can get, but with this combination you cannot get the 2E voltage, right? So that means you can get the 3E voltage, 2E voltage you cannot get, E voltage you can get, right? So that means voltage can be directly jumps from the 3E to E. So therefore, these kind of things are not preferred, right? So we normally have one combination like arithmetic progression. So 1 is to 2 is to, like voltages of 1 is to 2 is to 3 and so on, or 2 to the power of 0, 2 to the power of 1, 2 square likewise, and 3 to the power of 0, 3 to the power of 1, 3 square like this, right? So this is an arithmetic progression. So these are the geometric progression with the binary and the trinary coefficients. Right. So this is 1 is to 2 is to 3, this is 1 is to 2 is to 4, this is 1 is to 3 is to 9 is to 27, likewise. If it is 1 is to 3 is to 9 is to 27, right? You can get 81 levels in the voltage. Right? Understood. But the point is that if it is a 27, right? Let us assume this is the 27E, 27E, right? That means all the switches is supposed to withstand 27E voltage. Okay? So that is the drawback. Thing is that so we can increase the number of levels in the inverter by using this kind of things. So this one especially useful, or this is the best thing for application like the energy storage system. It is a bigger one, energy storage system or the PV, right? So we can directly integrate to the PV, right? We can directly integrate to the PV of, we can cascade this one, right? Or we can, this is scalable. If you want to increase this one, you can add one more H bridge, right? You can increase one more H bridge. Likewise, you can increase the number of levels. So let us assume it's 11 kV, for example, you're integrating to a 11 kV system, right? So 11 kV is the line voltage. So that means the phase voltage will be 11 kV divided by root 3, something you will get. Okay. So that means, so this voltage is supposed, these two supposed to withstand for 11 kV by 3. So that means, yeah, as a simple thing, right? For example, I'm designing for 11 kV some energy storage system. So usually, if you require, you or if you have 1000 volts on the DC side, all right. So there is some thumb rule is there, or some not thumb rule exactly, some proven thing is there. If you have 1000 volts on the DC side, so you normally get 625 volts on the AC side RMS value, right? So this is DC side, and you will get a 625 volts on the RMS voltage, right? So that means if you are selecting 1000 volts, right, you will get a, that means each switches, maybe you can use a 1.7 kV switching devices here if you consider some factor of safety as 1.7 or so. That is the thing, right? So that means accordingly you can adjust, right? It is 11 kV by root 3, right? Understood. So for let's I selected 625 has 625. So accordingly you can adjust this one. Let us assume if you calculate this one, you will get something like this, right? So that means it is 11 kV divided by root 3 divided by 625. So that is around 10. So that means you need to connect 10 H bridges in cascade, right? Each of 1000 volts, so that will generate 625 volts, all right? So that will be almost equal to a 11 kV system, right? That you can integrate to a 11 kV system, right? If you feel that the 10 is a small number, you may increase 20. If you are increasing to 20 means, so this 325 will become now 3 or 312, and this DC link will become 500 volts only. So now you have 20 H bridges in cascade per phase. So this is how it will be scalable to any voltage level. Right. So typically why it is especially useful, we normally connect some battery energy storage. If we can have some battery energy storage system, so we can connect some battery here. So obviously we have another circuit will be there for the charge. This is the actual battery we normally connect. So we normally have one more circuit here, or it will come like this. We have, it is a battery here. So we normally have some circuit like this, and you have another circuit like this. Okay. Circuit normally. Okay. And we normally have some capacitor. This is the bidirectional boost rectifier. So this is one switch, and this is another switch. So depending on the mode of operation, it will be from the buck mode or the boost mode. Normally this voltage will be higher when compared to the battery voltage. So this is the boost operation, and this will be the buck operation. This is boost, and this is buck operation. Okay. So this will on during the buck boost time, and this will on during the buck time. Likewise, it will operate. This is one more circuit. Or sometimes we use the other circuit, like if you require some isolation. In that case, we may prefer the dual active bridge converters. Okay. Understood. So this is how you can integrate to a battery, right? So if it is a battery energy storage is the bigger one. So in that case, we this is how we will use. Or also we can mix up the things, right? Let us assume we can also integrate several other things, like you can have the PV here. So we can also have the PV panel here. One PV is connected like this. Okay. So that is also possible. So that means this is how the hybrid renewable energy sources are there. So all these things are top one are all the batteries. So usually PVs will be more when compared to the batteries. The bottom one is usually like this. For example, 10 are there. That is 3 are the batteries and 7 are the PV. Likewise, depending on your requirement, all can be PVs, all can be batteries, or mix of PV and the battery. Right. So we have some algorithms, or we can control this one, whatever the PV power that produced here, right? So that we can transfer here, right? So that PV power you can transfer here, or we can directly inject into the grid, right? So we have a lot of control approaches are there, right? So this is especially useful for the grid integration. In other words, microgrid. Right, this is microgrid. So this entire, if you have a battery energy storage system inside, the PV is inside. So this will act like similar what we normally know as the synchronous machines, right? Synchronous machines virtually consists of some inertia. So that means some real power is stored, right? So this is also some real power is stored. So that means the entire things will be slightly different. The control of the means it is something like a lot of advantages you will get from this circuit. Okay. And another thing is that it is fault tolerant. So let us assume some fault, let's 10 H bridges are there per phase. So you have 9, if one is faulty, in that case, we can bypass this one, and we can reconfigure this cascade H bridge, or we can reconfigure the inverter so that we can operate. Right. So that's why this is especially useful when you're integrating a large PV or energy storage system. This is especially on another applications like the tracks applications, flexibility transmission systems, or the DStatCom applications, the bigger one. So this is useful. This is useful thing. Right. Uh, this is another thing, so which is the flying capacitor, multi-level inverters. So this is very much less popular, but hybridization of this one is slightly. We have some applications in the traction drive. It consists of some pre-charged capacitors. Right, these are some pre-charged capacitors here. Right, these capacitors producing some voltage levels, and this is especially advantageous in applications like the traction applications. In traction applications, we have so the one thing is that regeneration, right? So we have some regenerative braking is there. So during the regenerative braking, so whatever the kinetic energy stores in the wheels, so that energy we need to somehow store that, right? You know that kinetic energy, it is of mv square. So this is v is the wheel velocity, right? There are several other factors also there. That is, I'm just simply it is of mv square. Let us assume that, right? So before this is the energy stored. So this energy somehow we need to transfer. Right. So normally we use the capacitors. So that will capture the energy fast when compared to the batteries, right? So this is normally stored in the capacitors or the supercapacitors. So that's why these capacitors are used. This capacitor will quickly transfer or quickly store this energy, and slowly this energy is returned to the battery or other wherever we use that. Right. So why we need to do this quickly, right? For example, this is reduced by off, right? This velocity is reduced by off. That means you already lost the 75% of the kinetic energy, right? So that means you must be quick. So that is these capacitors or this ultra capacitor quickly store the energy, right? And they will store the energy, and they will gradually release to the other things like batteries or some other places they will release that energy. Right. So that's why it is especially useful for the traction applications where we have the frequent stoppages. For that, we can use this one. We'll store this one, or we can use this one for the other purposes, for the inside lighting or for other things. So most of the regeneration things work like that. So we are not fed to the grid. So most of the things, because the grid may be somewhere else, this is a small amount of power, right? The power may not travel that much distance because of these line impedances and all. So most of the times we store that in locally, right? Or else somewhere else, if it is a bigger thing, somewhere we have some stops for some other points will be there, or some things where we will drop that regenerative energy. Right. So this one is the hybridization. So that means is the cascade HP. So inside that we have the uh, means this one is the diode clamp inverters are there. So but it look like a cascade edge bridge. This is some hybridization techniques. Okay. So this is what the summary here. This cascade edge bridge are especially suitable for the application like the hybrid electric vehicles, photovoltaic power cells, uninterruptible power supplies, magnetic resonance images. Likewise, this is all of the applications here. Now this is self-explanatory. Okay. And next we move to the other topic. This is known as the Right. So this one is known as the reduced switch count multi-level inverters. The drawback with the conventional inverters are the number of switches are more and their complexity is more and other things, the blocking voltage of the individual switches are more, right? So therefore they deal with that one. We have a lot of research is happening right now. So every day we will find some new converter topologies that address some issues. So one issue is it maybe it will reduce the device count, or it may reduce the blocking voltage, or it may increase the modularity, or it may be more fault tolerant, and the power distribution among the DC sources. Let us assume that one major drawback with this cascade edge bridge is the uniform power distribution. Let us assume these are the batteries, right? So all these batteries must be charged and the discharged simultaneously. Or the another word, SOC level of these batteries is supposed to be same. One battery must not be undercharged or one battery must not be overcharged. The charge and discharges must be same. Right. So we have a lot of techniques are there like inter SOC balancing and intra SOC balancing are there. So these are slightly complex things. And also some active cell balancing is there. For example, one cell is excess, one battery is excess charge. Somehow we will transfer this excess charge into some other batteries. Right. That is one drawback of this one not exactly drawback, so one complexity so that we need to address. Right. So that is known as the equal power distribution, or in other words, equal utilization of DC sources or batteries, and voltage balancing, and the and nature of the DC link, requirement of bidirectional switches, and reducing the switching and the conduction losses. These are the objectives, so that motivates the researchers to uh, means develop some newer reduced switch count multi-level inverter topologies. Right. So a lot of things are there, or we can classify. It is difficult to classify all these things under one roof. So we can classify. We can try to classify into them like the symmetrical and the asymmetrical inverters, with separate and the level and the polarity generators, or something like that. It is better. I will show the uh, move forward, right? So this one is the separate level and the polarity generators. So that means the inverter is divided into two parts. One is the level generator part, and another one is the polarity generator part, right? So this one is the level generator. So this is responsible for producing the levels like 0 level, 100 level, 200 volts level, likewise. So all are one unipolar levels. So whereas this H bridge is responsible for converting these levels into positive off cycle and the negative off cycle. Right. Now I think you will understand, right? This is producing normally. If it is a H bridge, you normally require a DC, right? If you turn on these two, you'll get the positive voltage. If you turn on these two, you'll get the negative voltage, right? So that is how you obtain the negative this fair waveform, right? If this DC source itself is a multi levels are there, what happens is that So whatever these levels are there, these levels are, so this is positive half cycle, similarly you will get the negative half cycle. This is the concept. Alright. So that means the H bridge, we need to feed a number of levels, right? So that it will operate for both positive and the negative half cycle. This one is producing the levels. So we have several, all polarity generators remains H bridge only, but the level generator will be changed. So this is MLDCL, multi-level DC link. This is series switches and parallel sources. And this is the switched capacitor switches. And this one is the reverse voltage. This one, like several things are there. Uh, so this one is the T-type topologies. This is another thing. So we have, as we discussed, right? This one is T-type topology. This is the important thing, and this one is the cascade T-type. This one is the T-type module. Right? This is T-type single phase T-type here, and we can cascade these T-types, or else we can increase the levels here. Let's assume this is two DC sources are there here. So now we have three DC sources are there, and in between, so this DC link access through the these points, right? So we can have access through these points, right? So this is known as T-type. This is like improvement, and another one is the ladder-based structures. So this, for example, if you want some levels, right, it will be, you will need to traverse like this, right? Or else you can travel like this to, for example, this is starting point A, right? Or you can travel like this to get the number of levels, right? So these are ladder based structures, and this one is the level doubling networks. So we have some simple two level inverter. So this is cascade H bridge. So we cascaded these two together so that you can increase the number of levels. This is known as LDN network, level doubling networks. And another one is the hexagonal switch cell. I think, yeah, this one. A lot of topologies are with this hexagonal switch cell. So we know the H bridge, right? This is slight increased, improved version of H bridge. You have additional switches. You can see that, right? There are two DC sources, and we have some additional switches like H2 and H5 are connected, right? And also you have another source ER. So these things, in normally H bridge will produce three voltage levels. So just now we discussed, right? E0 and minus E. So whereas this one produces minus 5 is, means 5 levels. Somehow we need to bring these two in series, right? So that means if you're turning on this switch, or maybe for example, this is turning on this switch, and somehow the turning on this switch, right? And where else? Somehow we are properly operate this one, so we can add these two together, we can subtract these two together, and also we can add in the negative direction. So that means you can get ES plus ER, ES level, ER level, and minus ES minus ER, and minus ES minus ER level you will get. So that means if it is ES equal to ER, then you will get 2E. If it is E, you will get E 0 minus E minus 2E voltage. You will get, likewise you can operate this. Right. Right. So this one is known as a hexagon switch cell. So a lot of topologies are based on this one. So this is hexagonal switch cell. This is, if you observe that this is so far, this one is the T type, and this one is the hexagonal switch cell. We have just mixed all these things. But a lot of things are making here and there changes. That is, we have one side T type is there, and another side they are added the T type. Right. All these things will produce the different voltage level. This one is another important thing. This is switched capacitor. So here the objective is you have only one DC source is there, and remaining DC sources can be produced by the capacitor. So let us assume, if you consider, we have only one capacitor here, but we have the DC source here. And if you observe that, if you turn on the switch P, right, if you turn on the switch P, and you can see that this E and this S and P are complementary, this is off, right? And this source E and this capacitor both will be in parallel. Right, this is E here, and this is capacitor. See if you turn on the switch P. So now what happens is that this capacitor is also charged to E voltage. So now the capacitor is charged to E voltage. Right. So now what we do is that, so now we will turn on the switch S, right? So now we turn on the switch S. So that means we have the path like this. Right. So now we have this DC source and this capacitor both will be in series. You will get the 2E voltage. And you know this diode is just to prevent the short circuit of the this one, right? So therefore we connected a diode here. Right. If this diode is not there, so this capacitor is discharged through the switch. Right. So this one is right. So this is how we can increase the things, right? You can see this is the bigger one. So this P1, P2, P3, if we are all operated together, so that means this C1, C2, C3, and along with E, all these things will be in parallel. This is C1, C2, and this is C3, and we have the DC source. If we turn on P1, P2, and P3, right? Similarly, if you turn on S1 and S2 and S3, so all these things will be in series, right? That is C1, C2, C3 capacitor is in series with E. So you can bypass something, that is assume you can also bypass the certain switches if you all require. So these are producing only levels, right? So you require one polarity generator to produce the positive and the negative off cycles, right? So these are known as the switched capacitor topologies. Normally, it consists of some voltage gain, similar to the DC-DC converter. It normally consists of some voltage gain. So let us assume if it is there, right? So this is only E voltage level, but we are getting 2E, right? So this voltage gain we can there normally define as 2 is its voltage gain. There are several things are there. So all these things are based on the switched capacitors things. So all are based on the switched capacitors. Somehow, somewhere we use these things. This is also switched capacitor things. So where we can increase the voltage or levels. Right. Just we try to analyze. So once some circuits here. So this is level generator as we discussed, right? And this one, each one is a some sub module, and each one is some basic unit or sub module or like this. So this one, you know that, right? It's a chopper cell, the off-bridge cell. The operation is simple. So you're measuring the voltage between these 2 points. So when this switch S1 dash is on, so it is short circuit, you will get the zero voltage. So when this S1 dash is on, the zero voltage. When S1 is on, so you will get the VDC voltage. Assume all are same. VDC 3 all are same. VDC 2, VDC 3, which is equal to VDC. Right. So that means each cell is producing VDC voltage and zero. Similarly, this is VDC voltage and zero. All are like that. Right. So now we can have the paths like this. Let us assume you turn on the switch S1. Now you can go like this. Right. So now between these two, we are getting a 3 VDC voltage. All are same. Right. So that means if you are operating the polarity generator switches H1 and H1, this H2 and H1 dash, so that means you will get the positive VDC voltage. And if you turn on these two switches, you will get the negative 3 VDC voltage, right, like that. And if you require 2 VDC voltage, you can bypass one thing, you can bypass this thing, all right. So now I bypass VDC one. You can bypass anything like you have paths are there, like you can bypass this thing, middle thing I bypassed, or else I can bypass the last one, like this. Like, so now you can get only 2 VDC voltage. If it is a VDC voltage, it will be something like this. If it is just VDC voltage, you can bypass these two things. Right. If you require zero voltage, right? So zero voltage, this is the it is three switches are you need to turn on. Alternatively, if it is zero voltage, right? We bypassed all these things, and if you see that this is one way, or else you can turn on these two switches or these two switches. That also gives you zero voltage, right? So now we got the these voltages, right, like these voltages. So now this is the job of H bridge. So now if you turn on these two switches, you will get the positive off cycle. If you turn on these two switches, you will get the negative off cycle. So this is how a simple MLDCA will work. Right. So now where exactly you can compare is that you can compare with the cascade H bridge. Right. Compare to cascade H bridge, so we can using some lesser number of switching devices. Right. And that is the thing, right? So there is no clear cut advantages you can bet, but the advantages are some reduction in the number of switch counts. But there are a lot of disadvantages also there. So one disadvantage is that so these switches in this H bridge, right? So here the maximum voltage in this case 3 VDC, right? So all these switches must withstand 3 VDC voltage. So that is one disadvantage. Right. But the advantage is that so these switches are not operating at the PWM frequency. So these are operating at the fundamental frequency, right? So this entire thing is due to the turning on of H2 and H1 dash. So this is due to the H1 and H2 dash. Right. So that means during positive half cycle, so these two are on. That means this is operating at the fundamental frequency. But these switches are operating at the PWM frequency. Right. But the drawback here is that so these switches supposed to withstand this entire DC link voltage. Right. And another thing is that we can also have the different ratios like VDC, 2 VDC, and also we can try for 3 VDC likewise. Right. So if at all the voltage is producing, so we can get the different voltage levels. You can also see what is one. It works with 1 is to 2 is to 4. Right. But it may not work with 1 is to 3 is to, it may not work with different ratios like 1 is to 3 is to 9. Right. Normally it will work with 1 is to 2 is to 4 because it doesn't have the negative voltages, right? Whereas H bridge has negative voltages E0 minus E, so therefore you can subtract somewhere, whereas you can just add only, right? Either you can add or you can delete, right? Whereas in case of negative, you can add, subtract, and you can make it 0. So whereas this one it is not possible. So therefore, we normally have 1 is to arithmetic progression, that is 1 is to 2 is to 3 like this, or 2 to the power of 0, 2 to the power of 1, 2 square like this, but not this thing, 3 to the power of 0. This is not possible. Right? So this is only possible with the H bridge. Right? This is another thing. We'll quickly discuss this one. So this is same thing. So this is known as series switched series parallel sources. So everything is same. Only thing is that the level generated is slightly different. You can see this one. If you want this operation, you can get the 3 voltage. If you turn just we need, you can see observe here, right? So whereas here, if you require the full voltage, in this case, so this is the this is what the benefit uh, you got. Okay. So for this you need to, for example, you require 3 VDC. You can see these switches you need to turn on. So then you're turning on 3 switches. So whereas this one you're just turning on the switch S2 and S5 so that you got the voltage. Right. This is earlier you required 3 switches, so now you turn on only 2 switches like this. For example, you can also bypass. Let us assume if you want to bypass, you can bypass like this. So now also you need to turn on the 2 switches. That means if you compare these two topologies together, and you can say that it is having less number of switching devices. There also you require 6 devices. So here also you require 6 devices. But the point is that so we have the reduced number of switches, switching, right? For example, you require only one VDC, it will be like this. Right. So now also you turned on the 2 switches. Right. And another interesting thing here is that we can replace these things with capacitors. Like we can replace this with capacitors. Right. And if you turn on the switch S1 and S5, right? We turn on the switch S1. What happens is that this point is connected to this bulb, and this point is connected to this. So that means we have DC source here, and this is all these upper ones. I right now this one, right? And another capacitor. So all the capacitors bottom ones are connected to this DC one. Right? Similar, if you turn on this S3 and S4, so what happens is that the top ones are connected together. So that means, so this is how we can parallel the DC sources, right? So this is DC source. Now all these things will be charged to VDC. So this is VDC. So this is VDC, VDC, VDC. Likewise, right? Understood. So that means you basically require one DC source. So rest of the things can be means you can make the capacitors. Right. But there are other disadvantages are there when it is a capacitors. Again, if you are transferring some real power, the capacitor voltage will be reduced. Somehow we need to recover that voltage. So you have a mechanism that can naturally recover the capacitor voltage. Right. So these are other topologies are there. All these things, their main motive is same, and it is this is also another one. This is another topology here. This is what we discussed. It is T-type topology. right? So this each one is producing 5 levels here, right? So this is another alternative. It's a good alternative for the cascade bridge. You can have one battery here, you have another battery here. So likewise, you can work on, right? Also, you can have one PV, another PV like this, or you can do. This is we already discussed. And this is another T type with some slight extension. So all these things are just these are some extensions here and there. They're adding some switches here and there, likewise. So this is, I think we already discussed this. So this is another one. This one is the switch capacitors, right? So this one is producing 7 levels with one DC source, right? We have some capacitors are there. So by properly switching on this capacitor, so we can get the 7 levels. And this one is you see here, these are slightly complex here. This one is this entire thing is one inverter multi. This is all these things. If you observe that these are per phase circuits. If you are using a 3 phase, this is for one phase. All these things, whatever we discussed so far, are for the per phase. This is all thing is for per phase, right? So if you observe that this is not for 3 phase. Right, the circuit is not for 3 phase, right? If you want 3 phases, you have one more circuits like this. You have three more circuit, two more circuits. Like so this is another envelope topology. This is another invention. So with this, they are claiming that it is producing 25 levels. Right? But there are a lot of drawbacks are there. If the switches are less, but so many drawbacks here, right? Like these switches are withstanding the different voltages. So these switches is rated at some voltage, and these switches are rated at some voltage likewise. Right? For example, this switch, if you consider, right? So this switch, let us assume, or can anyone tell what is the blocking voltage of this switch? Or how much voltage that switch is supposed to block? So this switch, so how much voltage is supposed to block maximum? So let us assume the switch is off and the switch is on, right? You can see this DC source and this is another DC source, both are in series. Right. So that means this switch is supposed to block 3 VDC voltage. Similarly, this switch is supposed to block 3 VDC voltage. Alright. So whereas this switch is there, right? If nothing is connected here, so this switch, right? So this is supposed to block 4 VDC voltage and this is supposed to block 4 VDC voltage. These two will be in series, right? So we have different blocking voltages of different switches. So that will be complex, right? So these are all the different topologies. This is another one. If you see that this is a single phase, this is a 3 phase inverter, and this one they just opened up here, right? And they inserted this one, right? So this is one. It will increase the number of levels. They're claiming that it will increase the number of levels. Right? Uh, so any questions?
Srinu, sir. Yes, sir. Hello.
No. Questions?
In chat box, there is a question, Srinu. Chat box.
Hello.
No. Current source inverter, the same as we will use. Most of the times we use the
Hello.
GT boards. Yes, please.
Yeah, actually, you are telling that lot of IGBTs and devices is there. That there is harmonic blocks also. We can use it. That how it will be. The more harmonics will be fine. No, in a grid maybe in a grid bus, so that uh, it will be like it will be reduced or from the device itself or need to do any other things like.
No, from device there is nothing like harmonic reduction or something, right? The
Yeah.
inverter voltage waveform. So if the waveform is more close to a sine waveform, so in
Mm.
that case we can reduce the. So that means we are reducing the harmonics. So for example, I shown the two-level inverter waveform, right? That is some PWM waveform where the THD value is very much high, right? So if you want to
Yeah.
reduce that, so what you can do is that we need to connect some filters, or else we can go for the multi-level waveform. For example, this case, let us assume this case, right? This waveform, it's almost a sinusoidal waveform, right? So therefore, the THD is very much less, maybe 2%, 3% will be there. So further, if you are connecting some small inductor or some small filter, LC filter, very small filter, or the machine inductance, that is sufficient to means make it pure sinusoidal. So
Okay. So
depending on the voltage waveform, so we
mm,
can say that the harmonics are reduced or not. It is not depends on the switches.
okay, because of these switches, only the current harmonics will be distorted, right? Or
Not because
voltages.
of because of the switching, the current harmonics. This is because of switching it is happening.
Okay. So there are two will be there. No, one is for voltage distortion and is current distortion.
Yeah.
So because of this switching, it will have only the current distortion will happen at our grid.
So voltage switching, right? That
Yeah,
means the
yeah.
voltage distortions. So this
Okay,
is depending on your applications. Let us assume that your application is like active front end converter.
okay.
Let us assume I have one slide here. Right. Yeah. So let us assume that it is something like some application. Let us assume this is source, right?
Okay, source, generation
So that
source.
means this converter is operating as it is doing the job of AC to DC
Okay,
conversion,
okay.
right? So
Mm.
here what we have to see that these currents it is drawing, right? Right.
Correct.
It is
Yeah,
drawing some currents, right? So
yeah.
we can make these currents a
Mm.
pure sinusoidal,
Yeah, yes.
right? So we
Yeah,
can make this current pure
yeah,
sinusoidal, and at
yeah.
the same time we can also maintain this
The
DC link,
capacitor to filter.
right?
Oh, yeah.
Yeah. And on the other side, right,
Mm.
if you are properly control that, so we can make these voltages
Mm.
sinusoidal, right?
Okay. Uh, but in between of this switching, the current harmonic current will flow from load to source, right?
Harmonic current,
Will
this
flow.
doesn't matter, right? So whether the
Okay.
current flow is power is flow from here or here, the point
Okay.
is that this will sinusoid, this will sinusoid. Only thing is that the power flow is negative in that case.
Okay.
It will still it is sinusoidal, but
Mm.
it will be in opposite phase to the voltage. That's all. If the voltage is like this, right, the
Yeah.
current will be like this. Okay,
Okay.
that means we can compensate the reactive power. That means we can operate the unity power factor, and at the same time we can make it sinusoidal. If it is a reverse power, in
Mm.
that case, so we have the like this. This is voltage, and this will be the current. Okay. So every time it will draw the sinusoidal current
Okay.
and in phase with the voltage waveform, if at all, right? If you are making some change, if you require some reactive power, so then also we can deliver the reactive power. So those
Okay.
things maybe we can maybe the other resource person will discuss. So
Mm.
when he is discussing the current control methods like decoupled control methods.
Okay. Yeah. Yeah. Thanks, sir. Yeah.
Any questions?
I think time is 4. I think
Okay, if you have no questions, in the next section, maybe we'll discuss the more other aspects of the converters. So, like how to integrate the PV with multi-layer inverters, and also what are the challenges we have. So, those things we will discuss sometime.